absences in a row on March 1st.
I got it. All right. I had a student arguing with me about whether or not. I had a student arguing with me in another class that I couldn't do it more than once in one day, and I was like, I'm an expert at Top Hat. I know how to.
You released this idea to your linear class yet?
I don't know. I haven't done it in linear yet. I actually am. I value the time in linear. I have things to say in there.
Just periodically throughout the class, just be like, oh yeah, here's Top Hat. You'll get so confused.
Wait a minute. I value the time in here too. What are you guys doing? Let me start. Oh, he doesn't think I can because of the date. Like it one. I know. I mean, I know this. I was like, what if you had multiple meetings in one day? It's still, the software would still want to accommodate that, you know? Whatever. So exciting. Let's begin. Dear Father, we thank you for this day. I thank you for these students and for Top Hat and the ridiculousness that it brings us. Help us to enjoy this class today and to learn more about your creation, Lord. You know, I pray. Amen. So I don't know, whatever. Okay, so let me say a couple things. Number one, I described the process of finding the extension field. Theorem 25, for any field f of x in f of x, there exists an extension k of f, which is a splitting field for f. I think the argument, there was something in the argument we missed, because if you read Dumb and Foot, he talks about taking the intersection of all possible fields or something, and I don't remember us talking about that. So I think there was something missing in our proof. Okay, so I would just encourage you to read page 536 to think about what it is we left out there. But I want to focus our attention on is examples today. So just to give you a look ahead what we're doing, I want to try to wrap up section 13.4 on splitting fields as fast as I can, and at least say something about 13.5 today. All right, let's get to it. So here we have f of x equals to x cubed minus 2. All right, and we're looking at this as a polynomial over q, right? And then the question is, what's the splitting field for f of x, right? And another idea that was missing, I think, last time was we talked about adjoining root alpha 1, root alpha 2, root alpha 3, all the way out through alpha n, to get a field with adjoining alpha 1 through alpha n in order to split a given polynomial. But something I should have said is, and maybe I said it, but I don't remember saying it, is, if you want to kind of look at the intersection of, well, how can I say this? You want the smallest field that contains all of that stuff in it, right? I mean, so there could be some redundancy in those extensions, and that's why it could be at most n factorial, but generally speaking, for a given polynomial, if we have a polynomial of order n over a field, the splitting field is not going to be n factorial order, right? Actually, we saw that last time, right? We had a degree 4, which split with a degree 2 extension, right? Was it x to the 4th? I can't remember, plus 4 or plus 2 or plus 1? Plus 1. That was split. The splitting field for that was just q adjoin I, right? So it's a degree 4 polynomial, but it was split already at degree 2. And but he mentions that when we get to the next chapter, the Galois chapter, we're going to look at a generic polynomial. So there's this really cool construction of an arbitrary nth degree polynomial with sort of vague, not quite defined coefficients, and then finding the splitting field for that. And there, it actually works out that for a generic polynomial, the splitting field is n factorial size. So there is actually a context where it's always n factorial for a generic polynomial, whatever that is. All right, chapter 14, after the next test, right? And okay, so this, on the other hand, is a rather specific question. What's the splitting field? Now, why is it not q adjoin the cube root of 2, the real cube root of 2? right? Because this has f of x equals to x minus the cube root of 2 times what? Times like x minus, let's say, theta 1 times x minus theta 1 conjugate. Where theta 1 is, let's say, you know, the cube root of 2 times e to the 2 pi I over 3, right? So this is not a that's not a factorization in q adjoin the cube root of 2, right? Because this we can't actually do in this field, right? This is, in fact, x squared minus theta 1 plus theta 1 bar x plus theta 1 bar, right? That is in q adjoin square root of q adjoin the cube root of 2. I mean, that's a polynomial in there. So this is a factorization. This is a factorization in this field. It's just it's not split, right? I mean, because in fact this is irreducible as it happens. It's not obvious why that's irreducible, I think, but it is. So what do we need to do to split it? Yeah.
Did you say that that is in Q adjoining the cube root of 2?
Yes, but it's a quadratic.
Does it not have complex numbers?
It doesn't, because theta 1 bar is a product of a root and its conjugate. And theta 1 plus theta 1 bar is real. And this has to be because this is the field which picks up the cube root of 2 as a 0. Go for it. No problem. You're on YouTube, though. Is that okay?
Huh?
You're on YouTube. Is that okay?
Oh, yeah.
Okay, cool. We got permission. It's all good. Should have what?
Oh, so maybe you get confused.
I'm sure he looked at the board and was like, okay, I'm just going to go fast.
Oh. So this has to have, right? I mean, by construction, this has the factor here has to lie in here. Otherwise, the theorem. We had a theorem, right? That you guys are disturbating me. Let's see here. To use a technical term. So by construction, this was what? Like q of x. Curses. All right. So what can we do? What is missing, of course? And we also know that this, right? And this, like none of these are non-split, right? Because, by the way, the other two are isomorphic to the first one, right? So, and a theorem that I won't prove today, all right, is that splitting fields, if you found two different splitting fields for a given polynomial, they're isomorphic. So the concept of splitting fields is up to isomorphism. That's actually pretty hard to prove. It takes them about 2 pages of careful math to do that properly. And an appeal to Zorn's lemma. There's an argument by Artin on page 542, which is rather, wait a minute, 544 rather, which is rather delicate. All right, so none of these will work, so what do you got to do? Find something else, all right. And what is the degree of the splitting field? Let's call the splitting field K. K over Q is what? It's less than or equal to what? 3 factorial, right? So I think it helps to actually write explicitly out that, let me just draw a picture here. So here's like, let me make this not the unit circle. So here we got like cube root of, cube root of 2. Over here we have theta times the cube root of 2. Down here we have theta 1, theta bar 1. Oh, excuse me. I called that theta 1 and theta bar 1. All right, great. So what I'm trying to ask you guys is what is explicitly theta 1 equal to? So this is 100, this is 120 degrees if you like. 2 pi over 3. So what do we put there? That makes this 60, right? So it's what? I want numbers. I want numbers. How about like minus 1 over 2? And then what? Right. And then like theta bar 1 in my current notation, which is not his notation. It's just a notation I made up all of a sudden. Hope you can forgive me. So we're looking for, what are we looking for? We're looking for a field which has all of the roots of x cubed minus 2 in it, right? Up to isomorphism. But we can look inside the complex numbers because, by the way, the other thing that's stated without proof in this section at the end is the fundamental theorem of algebra, which says the complex numbers are algebraically closed, right? Any polynomial factors into a product of linear factors possibly repeated because the complex numbers are a closed algebraic field. So how can, what is it?
Have we learned what that means?
No. But we will, hopefully today. So, I mean, what it means in a nutshell is just this. Yes, let me finish this example here. So what's going on? How to get the splitting field? If we take, look at like, theta 1 over the cube root of 2. That's something that should be in the splitting field, right? But that's what? That's like minus a half plus I times the square root of 3 over 2. So apparently, theta 1 over the cube root of 2 plus a half times 2 is equal to I to the square root of 3. I'm not sure what's the fastest way to argue this, but I think it's fairly clear that K should include the cube root of 2 and I times the square root of 3. Look, there's a lazy answer to this question, which is the splitting field K is what? Q adjoin the third root of 2 e to the 2 pi I over 3 times the cube root of 2 and e to the 4 pi I over 3 times the cube root of 2, right? Because if you take Q and you adjoin this, this, and this, bingo, that's what? It's got all the roots, right? So it's going to split it. But what's the proper way of looking at that? What I'm trying to encourage us to see is that we could look at that as just being Q with the cube root of 2 adjoined, and then I times the square root of 3 adjoined. And let me do this further. So what's the, what is that? this field here. If you look at that, we have different subfields, right? So one of the subfields we have is just Q adjoin I squared of 3, right? That's over Q. But we also have these other 3 intermediate fields, like Q adjoin the cube root of 2, Q adjoin theta 1, as I've called it, or Q adjoin theta bar 1, right? And all of these are, in fact, also intermediate fields. So we've got all these different subfields running around in here. I root 3 is a degree 2 over Q, right? And these guys, these are degree 3, as we've talked about before, over Q. And what do we know about this? We know that the up top is a splitting field, a candidate for the splitting field of this polynomial, right? So it has degree what? At most 6. But it also has subfields of degree something that must, in order for this to, it has to be that there's a 3 here, and there has to be a 2 here, and a 2 here, and a 2 here, because to say otherwise would to not give you degree 6 up here, and or not allow you to divide the, we're forced to put those numbers here by the field extension rules that we have. Yeah.
So that tells us that Q adjoin cube root of 2 and I squared of 3 is actually degree 6.
Yes.
Not that it just could be, but that it actually
Right. So
is, because it's got subfields.
because of the existence of these subfields, that forces the degree of the splitting field, in fact, to be 6 and to be that. Again, up to isomorphism, because the concept of splitting fields up to isomorphism. Yeah.
So you said that it has to divide the degree of the top one, but what if you know the degree of
So what I'm
I root 3 over Q is 2? Why couldn't the other one
so
2 also, and then it would be a degree 4 or something like that?
let's see here. So we've got Q. Let me call the top one K. K over Q, right? It is equal to K Q adjoin I root 3 times Q I root 3 over Q on the one hand, like going that way, but also on any of the right paths, like this one, we have K over Q equals to K over Q adjoin, I said theta bar 1 in my picture. Could be any of those, right? But the thing is, we know that Q adjoin theta bar 1 or theta bar or theta 1 or the cube root of 2, those are all degree 3 over Q, right? So we know that this is 2. We know that this is 3. We know that this is some number at most 6, right? So you have a number which is at most 6, and it has 2 as a divisor, and it has 3 as a divisor by number theory. I would make a blanket claim by number theory. It must be 6. Okay? Yep.
I hope this isn't a stupid question. Why?
Well, there are no stupid questions, Liam.
That is not true. Why did you say theta and theta bar and theta conjugate? Like,
I wanted to emphasize that they're conjugate, as opposed to just calling it by this and that.
Okay.
They're
Because
equal.
by definition, those are conjugate, and so once you have the first
What?
root.
Yeah, this is the thing. When I start with a real polynomial, right, and I factor it, if it factors over the reals, then I'm going to have a product of distinct real factors, right? But if there's an irreducible quadratic in there, it must be that there's like conjugate pairs hiding in the details of that irreducible quadratic. Like I know this. And I think it's interesting to note when I find it. It didn't really do anything for our calculation, but it is interesting to notice that there's an isomorphism going from this field to that field, which is complex conjugation. So, questions? All right, let's go on to the next one here. In fact, this one example blows up into an entire section, more or less. All right, so here it is. Example, splitting field of x to the n minus 1. All right. And so let's see here. So, I mean, we've already done a fair amount of this example in class already this semester. Basically, the point is that x to the n minus 1 is equal to x minus 1 times x minus zeta, x minus zeta squared, x minus zeta to the n minus 1, yeah? Where zeta is equal to e to the 2 pi I over n, right? And of course, he pictures these on the unit circle. So so Q, he says Q adjoin zeta to the Q adjoin zeta, and he puts a zeta sub n on this to to tie it to its. So Q adjoin zeta n is called he calls it the cyclotomic field of nth roots of unity. Do you see why that splits? Why is that a splitting field for x to the n minus 1? I mean, here's the factoring of x to the n minus 1, right? And to generate any of the zeros in that field, if I have the principal nth root of unity, zeta n, I can generate all the other roots by powers, which of course is something you can do in the field, right? If I've got zeta n, I can get zeta n squared, cubed, fourth, fifth, all the way to the n minus 1th, right? So this has all of the roots of unity in it, and consequently is a splitting field for x to the n minus 1. Right? It can't be smaller than that, if you think about it, right? Remember, the splitting field is not just enough that it factors, it has to be the smallest field in which it factors. I haven't emphasized that enough, because it really hasn't been an issue in any of our constructions. But so then the question is, what on earth does that look like for a given example? I mean, how big is this really? And he tells us a little bit about that by studying the cyclotomic polynomial. So he says, in the special case that n equals p prime, all right, in the special case that n is equal to p and p is prime, then notice what we have is that x to the p minus 1 is x minus 1 times x, well, and I'll write it out, x to the p minus 1, how's this go? Curses. Dot, 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 dot. I know eventually we get to a plus 1 over here. I guess it's, is it just plus x to the p minus 2? Is it just plus x to the p minus 2? I forget. Does that work? Because if you multiply this by x, you get an x to the p, and then you get an x to the p minus 1, x squared and an x from the x times that distributing. And then the minus 1 gives me a minus x to the p minus x minus x to the p minus 1 minus x to the p minus 2, minus x minus 1 distributing through. So everything cancels out except for the minus 1 and the x to the p. Yeah, it's legit. And then the thing is, this is called phi p of x. This is the cyclotomic polynomial, which we proved, believe it or not, is what? It is, in fact, irreducible. That's right. So this is, in fact, irreducible. That is proved in an earlier section in Dummett and Foote. And so since that's irreducible, what's that say? That says that if we look at the cyclotomic field generated by zeta p over q, it has degree what? What's that? P minus 1, we have a winner. And the reason for that is because this is an irreducible p minus 1 degree polynomial for which this provides the 0 of. The 1 doesn't matter, that's already in Q. So, indeed. So, well, there's one answer. The cyclotomic field of prime order has degree p minus 1 over Q. What we see in the later section in Dummett and Foote is that if it's not prime, it actually ends up being Euler phi function over Q. So like this guy actually, as fun fact, in a later section we find out that if we have zeta n over Q more generally, the degree is the Euler phi function of n, which just happens to be p minus 1 when p is prime. So, as much as we love our initial example, we trade it for x to the p minus 2. Right? And look for the splitting field of that, where p is prime. What's it going to be? So if p is prime, of course we can factor this x to the p minus 2 as x minus the p through to 2, right? And then x minus can't draw it, zeta p through to 2. Let me call this thing theta. And then x minus theta squared. It's not theta squared. It's not right. Ah, curses. Fine. Zeta p squared, p through to 2. X minus the p minus 1th power of the pth root times the p through to 2. Surely I could have come up with a more clever labeling scheme than this. Let me call this one theta 1. Let me call this one theta 2. Let me call this one theta p. Seems like my numbering is off. P minus 1, yeah. Okay. So to find the splitting field of x to the p minus 2 over q, we need a field which does what? It has all of the roots of x to the p minus 2, right? And so I think the picture is very much like the one we have over there, right? We can understand it by basically, we've got, the p through to 2 and zeta p. That q, rather, not k. I'm saying k is equal to this. Q, I believe this is the splitting field for x to the p minus 2. because I think if you have the pth root of 2 and you have the pth root of unity, you can generate all of the zeros, right? Do you guys agree? If I have these two pieces of information, I can use sums and products and quotients to generate all of these. If you take the ratio of two of the thetas, you'll pick up like a power of, I mean, you take two any successive thetas, you take the ratio, you got zeta p in there. So the principal root of the unity has to be in the field, because if you take the ratio of, like, take the ratio of, say, this one and that one, theta 1 over the pth root, then you just get the pth root of unity. So the pth root of unity is in the extension field, in the splitting field. And of course, also the pth root of 2 is in the extension field. But my point is, if you have these two, you can also build this and everything else.
How do you get the powers of it?
Once you have zeta, you can square it, cube it. This is something we can do in a ring, right?
So like if you had Q join any number, then that number squared is also in.
Right. A field is closed under addition, subtraction, multiplication, division. So this is the process of closing the field. Like if you have a field that's sort of abstractly characterized in the sense that, like, you've got a base field and you've got elements you're adjoining, then the way those elements add together, subtract, multiply, and divide informs how that field abstractly is built. Like, sorting that out is forming the algebraic closure in some sense.
Then if you have, so like if you decided to, instead of zeta p, could you do zeta p to the p minus 1 instead, and that would be just as fine?
Oh yeah, yeah. Any relatively prime power. Because I mean, it is a group of order p, and it's a cyclic group, and so to get new generators, we must mind the new generators from old rules from last semester, all that fun stuff. All right, I'm digressing. So this is q over the p3 to 2 over q. Now over q, because x to the p minus 2 is what? Irreducible by Eisenstein. We know that this is degree what? Irreducible, right? So this is a degree p extension, yeah? But on the other hand, in this monstrous, well, it's not monstrous, this is a beautiful example. We have, q adjoin all these other fancy complex ones, like, pth root of unity times the pth root of 2. And, then q adjoin, let me just call them my theta 1, and q adjoin theta 2, and q adjoin theta p minus 1. You got all these subfields. And they're all, every last dumb one of them is degree what over q? They're all p minus 1 because they're all roots of the cyclotomic polynomial phi of x. So by the isomorphism theorem, between roots of a given polynomial, those are all isomorphic and degree p minus 1. Proof by Bethany. Let's see here. She said p minus 1. It must be true. Ha ha ha. Seems like we had some logic to that, though. I'm just joking. All right. So, and then check it out. But this one here is what? Splitting field. Now, see, I can't use quite the same argument I did last time. I mean, if you want to think about it, okay, so it has degree at most p factorial. Not terribly helpful, right? But the degree of the splitting field here is actually, and we can prove this, you guys tell me how, p times p minus 1 y. First of all, why does it have to be at least p times p minus 1? It has to be at least p times p minus 1 because it has a degree p subfield and it has a degree p minus 1 subfield. Right? So because it has these subfields, it must at least have p and p minus 1 as a divisor, the degree of the splitting field. There's no way you could get a p from the p minus 1 or vice versa. These are relatively prime, so they must both appear separately in the product, in the order for the splitting field. Why is it just that? Then it has to be at least that. Why is it just that? Why can't it be more? What is the splitting field? It's the smallest field which has all the zeros, right? This field has all the zeros for x to the p minus 2, therefore, that's it. So it has to be at least that because p and p minus 1 are relatively prime. It has to be at most that because it is already having all the zeros for the given polynomial. And so there you go, that's the splitting field.
So you know then for sure that k over q p through the 2 is of its degree p minus 1.
That is also true. So now you're mining further insight from this, which is great. See, the way you ask a test question about this to be maximally confusing is you ask a question like, based on, something based on like the irreducibility of some polynomial in here of degree p minus 1 or something. I mean, there's certain irreducibility questions that are related to this, right? I don't.
So the reason I ask that is because you just said that it's p to p times p minus 1. I now know that p minus 1 is what is from q p through to 2 up to k.
Right.
But how did you? I wasn't following exactly.
So how do I
know that it's maybe something smaller than both of those?
It can't be smaller than both of these because it has both p and p minus 1 as divisors. Because this is a subfield. I mean, all these are subfields of degree p minus 1 over q. And that's a degree p subfield over q. I mean, subfield of the splitting field. And again, by this same calculation over here, I can put, p through to 2 here, and I can put the p through to 2 here, and I know this one is p, and I know that, I don't know what that is, but I know that p has to be a divisor of it, and by the same logic, p minus 1 has to be a divisor of it. So p and p minus 1 both be divisors. They can't, neither one can get intertwangled in the other because they're relatively primed. Use technical number theory jargon there. And again, it's big enough because it does already split the polynomial. So, but you're right, once I know that, Liam's exactly right. Once I know that, as I wrote in purple down here, after I know that, then I can write these p's up here and this p minus 1 there, which are by no means obvious from the outset. Right? It's not entirely obvious that the splitting field over that is a degree p extension. I mean, okay. By the way, I'm sorry for doing the same example twice. Take p equals to 3. That's the first example. Right?
I have another question.
Ah.
That's literally just all numbers less than p, right? You said zeta sub p to the j.
Oh, yeah, you're right.
And I was confused by that because
Fair enough.
that's literally all numbers below.
Yeah, that's right. UP is kind of boring. Or to use the terminology of my son, boring. He'd be very annoyed if he knew that I had said that and attributed it to him just now. She'll have to make a mental note. This is timestamp. Let's see here. All right. Okay, so let's wrap this thing up here. So again, he gives arguments to prove that splitting fields are essentially unique. He defines the algebraic closure. All right, what is the algebraic closure? The field F bar is called an algebraic closure of a field F if F bar is algebraic over F. And what else? And if every, goodness gracious, every f of x with coefficients from f splits completely in f bar. He says, in other words, f bar can be said to contain all the elements algebraic over f. Furthermore, definition, a field K is said to be algebraically closed if every polynomial with coefficients in K has a root in K. Proposition 29 says let f bar be an algebraic closure then f bar is algebraically closed. So do you see the distinction? I mean, there's two definitions kind of using similar sounding words right above what's written in black. What's the difference in concept here? So every polynomial splits completely in the algebraic closure. Well, an algebraic closure, right? There could be more than one. Versus a field K is said to be algebraically closed if every polynomial with coefficients in K has a root in K. So proposition 29 says, let f bar be an algebraically closure, then f bar is algebraically closed.
So is F bar, is it a splitting field? Is F bar a splitting field?
F bar is a splitting field for every possible polynomial in F with coefficients in F. I mean, so this says every polynomial splits completely, right? So this says that every polynomial splits like entirely, right? It means it split linear, right? Well, if you think about what that means, So to show it's algebraically closed, I need to show every polynomial with coefficients in k has a root in k. Well, just pick your favorite linear factor and plug in the root there. It's going to be 0. So I think proposition 29 and the two above definitions are essentially this thing we have struggled with in calculus, well, not calculus, pre-calculus, right? The distinction between factoring and plugging in a root. Top is about the existence of a factorization. The next one is really about the existence of the 0 corresponding to that factorization. But it's stated in kind of a lazy way in the sense that there just exists one, right? Because if there exists one 0, then you can get, right, n possibly repeating if you sort through it, the mechanics of the polynomial factoring. But anyway, let me just summarize what the section says. So if you start with a given field and then you try to form the algebraic closure, that's really kind of staggering, like what that amounts to, because you're thinking about all possible. I mean, if you fix a polynomial, you want to find the splitting field, that's relatively clear calculation. But what if you want to do that for not just one polynomial, but for all possible polynomials? As Dummett and Foote describes, he's like, that's a terrible bookkeeping problem. It can be done, right? But then that argument on 544 uses a kind of sneaky trick to find a way of taking a given field in all possible polynomials and finding this larger uber field in which all polynomials split. So that gives you a construction of this massive splitting field that splits everything all at once. But then because splitting the concept of, this concept is up to isomorphism, it basically says, hey, there exists this algebraic closure of a given field out there somewhere that you can work with for arbitrary fields. Now, pragmatically speaking, we're always working with what? Almost always Q, right? Or something like that. So we actually can take our sort of uber universal field that we're working inside of to usually be complex numbers, right? Because the complex numbers are an algebraic closure of the rationals, right? They're also an algebraic closure of the reals. And he has another theorem here about that. He says, if the field C contains an algebraic closure for any of its subfields, so you pick any subfield of the complex numbers, be it reals, rationals, or other weirder stuff like Q adjoin the cube root of 2, cube root of 3, cube root of 2, right? Those are all subfields of the complex numbers. Their algebraic closure is, again, inside the complex numbers. So the complex numbers is playing the role that very fancy theorem by Zorn's lemma described in Dummett and Foote plays.
Okay, wait, you said C contains an algebraic closure.
I said that, I'll read it carefully. The field C contains an algebraic closure for any of its subfields. In particular, Q bar, the collection of complex numbers algebraic over Q, is an algebraic closure of Q. He says, the point of these considerations is that all computation involving elements algebraic over a field F may be viewed as taking place in some large field, namely F bar, and we can speak sensibly of the composite of any collection of algebraic extensions, viewing them all as subfields of a given algebraic closure. So this is important because sometimes when we're like starting in a kind of abstract context, we're kind of building our way up from there, you might worry that what you're building your way into doesn't exist. But this is comforting. It says that we can construct extensions and put them together, and they're all fitting inside something, even if we don't have a name for that thing. That's so. And then up next, section 13.5 is on separable and inseparable. That is, the whole point of that section is to explain how do we deal with repeated roots carefully. This is something I don't think I did do at all in 421, right? So, oh, yeah, better stop. We'll talk about that next time. And yeah, we'll move the test back a day. That's fine. Yeah. If you want to turn in, as soon as you turn in your homework to me, when you're done with it, you email me, I send you the solution.